Good afternoon, ladies and gentlemen. Welcome to today's lecture. This is Thursday afternoon, the 1:50 lecture. All right. So today we will be discussing collision handling. We've already discussed hash functions, and we told you that based on the hash function that we were using, there is a potential for a collision. So if you hash a function, you'll get the same position out for two different values. Today we're going to discuss how to handle that. Now there's a few ways in which we can handle that. But before we do that, I just want to make a few announcements. We will be sending out an email today to all the students that need to apply for the SSA. Please note that we accepted all submissions until 1820. If you submitted after 1820, your submission is rejected. Now, I've warned you guys before, that 1 hour you get to submit is for you to submit. You will know in the first half an hour of that hour if you have a problem submitting, and you can let us know. If you did not let us know, then that is up to you. So if you submitted after 1820, which is already 10 minutes after the time we close the submissions, your submission has been rejected. You will receive an email stating that you must apply for the SSA. Unfortunately, we can't extend this indefinitely. It means you had 4 hours and 20 minutes for a 3-hour paper. That just doesn't happen. You guys need to get used to the fact that you need to manage your time a bit better. Like I said, we had an issue and he emailed us and we handled the issue. So this only applies to the people that didn't contact us at all. They just simply uploaded late. Some of you uploaded an hour late. It's definitely not being accepted. But if there's any issues, once you get your email, like I said, you will get an email. You'll see that there's a status on Eve that indicates whether you need to apply. If your paper has been submitted, it will be empty. If you need to apply for the SSAs, it will say apply for SSA. Then you can contact us to find out if there's an issue. There. The peer review for the projects, I believe, have been extended until midnight tonight, or is open until midnight tonight. Please make sure that you complete the peer review because that does affect your mark. And then there was one more announcement. Dr. Cottrell, what was the other announcement?
The mute button. There is the team feedback. There's links for feedback for your team and for anonymous feedback on the module. You'll also have to do a teaching and module evaluation again by the university. The anonymous one is more for what you think we should change or improve. It's anonymous, we won't know who said what, so you can feel free to write what you like, just keep it somewhat PG. And the team feedback is just asking a few questions about the project. The emails will be sent out today, yes, as soon as the lecture is done.
Okay, so please do the module and teaching evaluation. It does help us. It allows us to see where we need to focus our attention. For instance, in the last one, it was pointed out that you're a bit. We take a bit of time answering questions in Discord, which helped us because we looked at that and then hopefully we improved on that. So we can see if that has improved or not with the next review. So yeah, reviews are for anything, module, teaching, anything that goes on in lectures. It's basically just, I wouldn't say criticizing us, but kind of either constructive feedback or just feedback, whether you enjoyed it, whether you did not enjoy it, is it boring, is it fun, anything that you feel is relevant towards the course and towards us as lecturers teaching you. Not personal, I guess. I guess it can be as well, but like Dr. Cottrell said, just keep it PG. Right. Your peer reviews, you can go wild. And for the anonymous review, the informal review that we'll be posting, which is also anonymous, you guys can go crazy there as well. Right. Now, on to today. Collision handling. So the first thing we need to look at is what are we going to define, or what hash function are we going to define here? So I've listed the very simple algorithm we're going to be using as an example. So you can see I'm using the prime number division remainder hashing algorithm. And that uses the key and we're modding by 7. So the prime number we're using is 7. Please note there's a range of prime numbers that you can use. I'm just using a smaller prime number here so that the display looks nice to you and so that we can run through a few examples so that you can see what will happen. Right. So this is our input table. There are a few additional values that the screen wasn't large enough to fit everything in and still kind of look okay. So these are the values that I'm going to be using. You can see on the left-hand side, we've got the key. Now the key is what we're going to hash. And then we've got a car model, and that is the information that we want to store. So the information we want to store is the information that's going to go into the hashing table. And the key is going to determine where it's going to be placed inside that hashing table. Just get my mouse here. So when we apply the hash function to our table, you'll see that the positions we get are positions 1 to 0, or 0 to 6 essentially. And then you'll see at the bottom that we've got the Audi, Chevy, and the Hyundai. It also has a 1, 2, and a 3. But those positions are already filled. So the question is, how do you handle that? Because that's now a collision. How will you handle these collisions? Now, the first thing you should note is we are indicating that there's only 7 spaces, and we're not going to address the situation of you running out of space. There are special algorithms out there that will dynamically increase the space of the hash table as it starts running out of space. We're not going to look at that situation. We're simply going to look at the situation that we have a number of inserts we're going to be using, and then in the order of the inserts, how do we deal with them? So in this case, I'm telling you there's only 7 spots. So one thing you will have to keep in mind in your exam, will tell you there are 7 spots, or 10 spots, or 11 spots available. It'll tell you specifically how many spaces there are, because that is important. That is what you'll be using. It'll also tell you what to use as your hashing function. And most of the times, it'll give you a function where the prime number is also the size of the available spots. So we'll talk about that tomorrow afternoon and tomorrow morning when we discuss one of the past papers. But essentially, we will give you the size. So you don't have to worry about choosing the prime number for the exam. So in terms of those collisions, how do we handle them? So there's a range of algorithms that we can use. We'll be discussing 5. So we've got linear probing. We've got a 2-pass file creation. We've got a separate overflow area. We've got a synonym chaining. And you've got a bucket addressing. We'll look at each one of these individually. So linear probing. So linear probing searches for the next available spot. And what that refers to, it looks at the input. Now, on the left-hand side, you can see we've got a table with a key and the model, the information that we want to store. And I've already applied the hashing algorithm to those keys. So you can see it goes into position 1, 3, and 2 there, respectively. We want to insert these into the table on our right-hand side, which is going to be our hash table. So how do we handle this? When we look at them, you'll already see that Audi has position 1. Position 1 has already been filled. So linear probing is literally about testing the next available position to see whether there is an open spot. So we look at position 2. You see position 2 is open, so we place Audi down. So the insert of Audi has been dealt with. It's successfully in our table with linear probing. Then we go on to the next one, Hyundai. Position 3. Position 3 is open, so we can place it into position 3, no issues. Then we've got Chevy. Chevy wants to be placed in position 2, but position 2, once again, is full. So with linear probing, we test the next position. The next position is also full, So what we do then is we just continue on probing until we find an open spot. The moment you find that open spot, you can place your results into that spot. That is linear probing. So it's literally, you hash the key, find the position. If the position is filled, then you test the next position. If that position is filled, you keep on testing until you find an open spot. Is everybody comfortable with that? All right. So in your tests and in your exams, there will always be an available spot. Like I said, we're not going to discuss what happens if you run out of space. So in the examples we give you, there will be enough space. But there are, like I said, there are algorithms out there that deal with the load of a hash file. So when the file starts filling up, it will dynamically increase the size of the file and create more spaces. Like I said, we're not going to discuss that right here. All we want to know is the algorithms we can use to handle collisions. And in the exam and in the test that we'll have you evaluate, is there won't be a situation where there will not be enough space. There will be enough space. You'll most likely fill the table, but there won't be a situation where you've got 11 records to insert and only 10 available spots. So aside from the available space question, is everybody happy with this specific algorithm? No. So collision handling handles a collision. It's not an error. It's a error handling is when you know something in your program is going to break. So you need to make sure that you catch that specific error, that you don't break the system. So for instance, if you're asking for an input from the user and you're asking for a integer input and the user gives you a alphabetic or a character input, that will break your system. Now, in terms of inserts, if you're going to try and insert something into a spot where there's already information, it will simply just override that information. So this is more to do with you having to check whether there is something there or not, and then dealing with that. So collision handling and error handling are two different things. Don't confuse them with one another. Because when you start talking about hash tables and hash functions, you deal with the data structures differently. Because it's not an error anymore. It's more of a check of if there is information, then something happens. If there's no information there, then something happens. So it's not an error. An error is when your program is going to break. It's going to cause an issue. Yes, a collision is a clash. So for instance, it's like you walking into a venue and you want to go and sit in a specific chair. If the chair is taken, you just move over to the next chair. No issues. If you walk into a venue and the venue is on fire, you're going to go and sit in a chair. If you're intelligent, you won't, because you'll probably burn. But I mean, if the venue's on fire, you're not going to be going into the venue to sit on the chair. But if the chair is open, or if the chair is full, and someone's sitting there, you're just going to go to the next chair. Simple example, and it kind of, I think it kind of makes you understand what I'm referring to. You'll be surprised. In our first year, we wrote a class test, just a class test. The fire alarm went off, and everybody was still sitting there writing their classes. The lecturer actually had to shout at us. It was Prof. Lowe. Had to shout at us for focusing more on our class test than the actual fire alarm going off. So I wouldn't necessarily say no students that dedicated. Regardless. Going on to the next one. If you say constraints and restrictions, what are you referring to there? Because it's literally the idea is you find the position, so you hash the value, you hash the key, find the spot where you want to place this value. So you search the position. If the spot is open, you place it in. If the spot is filled, you search for the next available spot. Now, let's say the result is position 6. Let's say it's position 6. And what will happen is with your increasing value, position 6 will go and start probing from position 0. So it literally moves to the last position. If that is filled, it starts from the top and goes down one by one until it finds that open spot. So in terms of constraints and restrictions, there's not really much with linear probing. It's like an array. If the slot is not open, you search for the next slot that is open and then place it there. Okay, moving on to the next one. So the next one is a two-pass file creation. So just to double check, you all understand what linear probing is now, right? If I give you a class test about linear probing, you should be able to do it now, right? Okay. Now, two-pass file creation. The easiest way for me to explain two-pass file creation is like this. You're basically applying linear probing once after you successfully inserted everything that can be placed. So let's go through this, and then the moment we go through this, you'll understand what I'm saying a bit more clearly. So, two-pass file creation with hashing. So, store records in a hashed position if empty during the first pass. So what that refers to is the fact that you're going to go through this hash table first. And you're going to place every single value you can where there is no collision. So you don't apply linear probing yet. You just simply try and place everything that can be placed in a spot. If there is a collision, you don't place it. You keep it one side. Then the second pass. So the second pass, you create a second file. What happens in the second file is the fact that you take everything from your first file and you put it in your second file, and then you apply linear probing to whatever is left over. So to show you the result, if we go back to the first table, you can see we've got Porsche Ford. Let's just look at the collisions here quickly. You had Audi that had a collision with position 1, so that was placed in position 2. You had Hyundai, no collision, so that went to position 3, and you had Chevy that was meant for position 2, but because of linear probing, Audi was placed in position 2, so now it was placed in position 4. Now, with a two-pass file creation, what will happen is we'll place those values first. So Audi has a clash with Ford. So Audi will not be placed. It's kept on one side for now. Hyundai, no clash, it's being placed. Chevy, no clash, it's being placed. So that's the result of our first pass. Audi had a collision with Ford. So it was kept out of the first pass. The second pass, you apply linear probing. So what happens here is now you try and insert Audi. So you go and you hash Audi, you see position 1, and then you apply linear probing, just searching for that first open spot. Now, the difference between linear probing and two-pass file creation is the fact that you get more values that are supposed to be in their original position than you get with linear probing. As you can see, Audi is the only one that's not in its hashed position. It's the only one that's in a different position. If you look at the previous table, or with linear probing, you'll see that Audi and Chevy are both not in the original hash table values. The two-pass file creation gives you that benefit of having more values in their original position, or their original hashed position values. So the first time you go through the table, the insert table, you place everything that has no collision. If there's a collision, you keep it one side. The second time you go through it, you copy what you have in the first hash table into your second hash table, and then look at everything that's left over from your insert table, and then apply linear probing to that. So it would be better to do the two-pass file creation than the linear probing. Depending on the size of your data, yes, because you've got more values in their original position or their hash position. You're only focusing on the inserts. You're not even looking at the removal. Because what happens, let's say I remove, if you go to linear probing, let's say I remove forward. Now, when I remove forward, what is supposed to happen is that position is now open. Audi is in position 1. So when you search for Audi, you're going to hash the key value, and you're going to search for Audi in position 1. If there is something there and it's not Audi, then it's going to start looking for Audi going down one by one until it finds Audi, or until it does not, or until it's reached the end of the search. It will go through this file at least once completely. So what will happen is after you remove forward, you would have to go through this file and check what could have gone into that position and then put it there. But now, if you look at this entire folder, you'll see that Audi and Chevy will have to both move. Now, with the two-pass file creation, if you remove forward, it's only Audi that's going to be placed in that position. Chevy is in the position it was hashed in, so there's no issues there. So it has its benefits, but it also has its disadvantages. That just depends on the application of it. All right, question before we move on to the next one. Debe? Oh, okay. We'll just take that away then. If you could just kind of drop your hand. Okay. There we go. You have a question now? No. Okay. I think you just accidentally dropped it when I dropped it as well. All right. Moving on to the next one. Separate overflow area. Now, I'm first going to ask you, what is an overflow? How many of you can tell me what is an overflow? How would you describe an overflow? Let's say you have a bucket, you fill it with water. What happens to an overflow? It's an excess, yes. It spills over, spillage, yes. Go beyond, yes. So an overflow is exactly the way it sounds. If there is a collision, now looking at these studies again, if there is a collision, in this case, you know that that Audi has a collision with Ford. Hyundai and Chevy will place with no results. So what's going to happen is once it's placed the results, it sees Audi has a collision, so Audi will go into a separate overflow. It doesn't fit into its hash value. So the overflow is literally, if there's a collision, it just gets placed into the overflow. And the overflow is handled one at a time. So it's not like linear probing where you search for the next available spot, you just simply place it into a overflow where it doesn't even keep track of the value position. So if there is a collision, it will then search for the information inside the overflow. But then it's not based on a position. There's no tracking that information. It's literally just excess. It just goes into that overflow for later usage. All right, just want to look at a question. Looks like something applying to the previous one. The two-file creation, since we'll be copying data from the first pass file to the second one, will that not take up a lot of space if we are dealing with a larger amount of data? Now, there's two ways in which you can deal with this. Two-pass file creation is you go through the information once, you fill the information inside your file, and then you go through the inserts again, and whatever didn't place on the first time, you now apply linear probing on the second time. It refers to the fact that you still actually have your original file, you now just place the results after that. Now, a lot of people are not in favor of this. So there's a second method as well, where you take the original table and you create a second file with linear probing applied to the second file. What the original intended algorithm was, it's a two-pass file creation. So it's one file, it's not two files. There are solutions where people create two files. The ideal solution is one pass, place in the file what you can place in the file, do a second pass and apply linear probing to that one file. Now, when you do it in the exam, we expect two tables. Table 1 that represents the first pass, table 2 that represents the second pass. So why I tell you two files or two creations is because I want you to remember the fact that you need to show me two tables. Otherwise, you're probably going to show me the second pass table and lose the marks for the first pass creation. So essentially, it is only one table, and your final result is that the result of that final table. And I won't be showing you this in code. This is drawn in an Excel spreadsheet. So the way you see it on my screen right now is how we expect you to draw it in the exam. This is not practically tested of you, because you have to keep in mind that if you have these, so all of these are based on random access. You have to first go and check if that spot is open. Is there information there? If there is no information there, then you deal with it, and then the overflow, the additional files, or whatever else is needed. Unfortunately, we don't have enough time to do them practically. I would love to, but it's just not enough time. It's not relevant as well. I'm just telling you how to deal with collisions so that you are aware of it. You will be doing collision handling later on in your undergrad course. So you will eventually do it, but you're just not going to do it in 1P practically. All right. So everybody happy with overflow? If there's enough time tomorrow afternoon after the chat, after we've gone through one of the past papers, then I'm more than happy to show you that. But I'm just warning you, it takes a while to set them up. It's not something you're just going to code in 3 minutes and then it works perfectly. Right. So everybody happy with the overflow area? Can I move on to the next one? All right. Looks like you are all happy. The next one is even more fun. Yes, the overflow is simply just a repository. Well, if you say repository, I would rather describe it as a stack, no, as a queue. You literally just pop them in one by one. So what will happen is if you have a collision, if you're searching for something, if it's not in the position where it should be, it's going to search the overflow one by one, going through all of them. So no specific positions thereafter. So you go from linear probing, going down one by one, searching for them one by one until you find them. And in that case, let's say you look at this table. Audi is not in position where it should be, and Chevy is not in the position it should be. So if you search for Chevy, which should be in position 2, you now have to go down 2 values. And Audi, you have to go down 1 value. So the moment you have to search for both of them, those are 3 probing searches that you have to do. If you do that in the phase collision, you've got Ford, which you have to probe 3 times, 1, 2, 3 times to find Audi, but the rest of the information is where it should be. So no issues. With overflow, everything is there. If you've got a collision in Ford, overflow first item. So it can improve your search algorithms to get you that information a lot quicker. Because what it will do, if there's a collision, it will go straight to the overflow. So when you're searching for it and it's not there, it goes straight to the overflow and then searches the overflow. It doesn't have to probe one of these spaces one by one to find it. So now if you do a lot of inserts here, let's say I do 2 more inserts and they both clash here, then the search gets a bit longer. Because now it's not just potentially, let's say I've got a clash with Hyundai, I put one down, it's now Hyundai, check overflow, okay, it's not Audi, check the next one, if it's that one, if it is that one, then I can retrieve the information. Otherwise, it's not in my file or in my storage. So there's a lot of different situations where it can be applicable, but in terms of overflow, it's literally just you dump it into a file. You can see it as a sequential. So you've got a random access file. If it doesn't fit in that spot, then you place it into a sequential file, one after the other. And in order for you to find something out of the file, you literally have to search for it one after the other. Right. Then, synonym chaining. So the overflow, if I go back here, the overflow you see doesn't have an address. It jumps directly from collision into the overflow, and then you have to search the overflow. You don't know where it is. You have to search the overflow. If you look at synonym chaining, what this will do, and you'll see I added a few more info spots here, just so we can kind of get the feel for it. Audi, we already know has a clash with Ford. Hyundai will play successfully. Chevy will play successfully. Tesla is going to have a clash with Chevy. And Suzuki is going to have a clash with Ford. And the next spot is going to have a clash with Audi. Synonym chaining looks at a pointer. So where you had the overflow is literally you're just dumping it in there. Now, synonym chaining has an overflow, but a pointer to the file that you want. So for instance, Ford. I insert Audi. Ford has a clash. Now it places it into the overflow, but a pointer is placed with Ford to say that there is a second value. There was a clash, so there is a second value, and it points directly to the second value. It's not that you have to go start probing the files or the spots one by one. And it's also not the fact that you have to search the overflow one by one. It literally tells you, okay, there's a clash. There's the next position that had that position, or the next piece of information that had that position. So that's Audi. Then you had Hyundai that plays successfully. You had Chevy that plays successfully. Then you have Tesla. Tesla clashes with Chevy, so it places a pointer to where Tesla is being put. So when you go to Chevy, if you're searching for Tesla, it's going to see Chevy. Okay, Chevy is there, so it's not Tesla. There is a pointer. Take me straight to the next position. Okay, there is Tesla. No issues. I don't have to search the overflow. It takes me directly to the next information of that position. Then we have Suzuki. Suzuki clashes with Ford. So it takes the pointer. Okay, there is a pointer already there. So it goes to the next pointer, Audi. Then it places it in the file and places a pointer next to Audi saying the next position 1 is in the file and to where it is in the file. Now, you can have any number of pointers. It just depends on how you set it up. It depends on your size, what your size limitations are. But you can have, this entire file can be a pointer for position 1. But then, if that is the case, then there's probably a better algorithm to deal with that solution. So there's no limit here to how many pointers you can have, because it points to the next one. And when it gets to the last one, you'll see Suzuki, there is no to the next one. So that is the last item for position 1 in this synonym chaining. But the idea is that it goes over into the file, but it points directly to where it is. You don't have to search for it. Everybody happy with that one? Okay, so you guys are you all still with me? Guys and girls. If I mean guys, I mean it as a collective. All right. Now, going to the last one, bucket addressing. Now, bucket addressing has an additional requirement to it. Bucket addressing refers to the fact that you've got a bucket, and your bucket has a size limitation. Now, if I say a bucket, you can see this as a two-dimensional array. So you've got position, let's say you've got your columns, you've got your rows. Buckets are how many clashes you can handle. So it's how many open spots there are for a specific position. If it fills up the positions there, then it is an issue, and that, like I said, there's algorithms to deal with that. So we're not going to look into that. But the thing you need to know about bucket addressing is the fact that you have bucket sizes. How many clashes can it handle? So I'm using the same table as the first table. So you know we've got 3 for position 1 and 2 for position 2, and the rest placed in quite comfortably. So bucket addressing looks at the item, looks at the position, goes to the position. If it sees that position is full, it goes to the next position. So it literally adds it to the bucket on top or behind the first one. I say on top because if you fill a bucket, you fill it from the bottom. But the idea here is that you've got Ford. Because Ford is there, Audi can't be placed there, so it goes to the next bucket address. So it goes to position 1. If you're searching for Audi, it goes to position 1. If Ford is there, it goes to the next bucket item in that list or in that position. And if it's not there, it will continue until it finds it or until it reaches the end of bucket size. So remember, there's always a size with buckets, and that indicates how many records it can handle. So when we place all of these results, your input would look as follows. We'll have Ford. Audi has a clash with Ford, so it places it into the next bucket address for position 1. Hyundai, no clash, it places. Chevy, no clash, it places. Tesla has a clash, position 2. So it goes to the next bucket address. It is open and it places it. Suzuki has a clash with Ford. It goes to the next bucket address. Has a clash with Audi. Goes to the next bucket address. Sees that it is open and then places it into that specific bucket. Now, we still have one bucket space available here. So in this case, we had a bucket size of 4, allowing us to add 4 clashes. In the exam, we won't give you something that exceeds the bucket size. So you don't have to worry about a situation where what happens if these buckets are full. Yes, it's the size that you dictate. So you're going to say there's a bucket size of 3 or 4, and then after that, you'll probably have to use a different algorithm to deal with it. So this is just one of the concepts. The algorithm that will most likely be used to deal with this is by increasing the bucket size limitation. Like I said, we're not going to discuss the situation where you run out of space, because that's an entire different set of algorithms. Because there is, if I remember correctly, it's called hash files load function or load balancing, where it makes sure that this file never actually becomes complete. So the moment that this file is at about 80% capacity, it will start increasing the size of the file to accommodate the others, because you don't want it at 100% capacity. Like I said, we're not going to discuss the situation of what happens if you run out of space, because that's not what we're interested in. We're interested in how you can deal with clashes specifically. Will I be correct to say that the bucket addressing is more like the previous one, but with records instead of pointers? Yes. So in this case, you've got a separate file, and it points to that separate file. So if if we had to explain this in terms of random access, you would have position. So you've got position 0 to 7 in your one random access file, and you'll have three data indicators. You'll have position, you'll have the model. So you'll probably have key position, key determines the position. You've got your model, then you'll have a pointer. Then you'll have a second file. The second file will store your information, so you'll probably still store the key. You'll store the model, but then you'll store the pointer to that file. So what will happen is you'll probably go, Ford has a clash, 40 has a clash, so it goes to the file, looks to where it can place it in the file and see it's being placed in position 0 for that file. Goes back to the first file and says, pointer position 0. So it will tell you in the new file, position 0 is the Audi. And then when you play Suzuki, it will place a pointer, but that pointer will point to this file. So it will say Audi, but it also has position 1, but now the pointer will go to position 2. So when you search for something in position 1, it will go forward, okay, not what I'm looking for. Look at the pointer, go to that specific spot. Audi, okay, not what I'm looking for. Look at the pointer and go to that specific spot, and then there you have it. In this case, the pointer is something that you would have to deal with. It's something you would have to manage as the coder. That's why we're not doing this practically, because it's going to take too long for you to do every single one of these and understand it perfectly in terms of applicational code. Bucket addressing is more of you have your position, you have your model, and then in your record, you'll have position 1. So let's say you've got your data structure. You'll have data structure 1, data structure 2, 3, and 4. And position 0 is 4 times that data structure. So when you reserve that space, you'll reserve 4 empty spaces and then fill it up like that in your file. So it's not a pointer to a second file or a second location. It's more of a fact of going to position 0, looking at the first item. If it's not in that item, look at the second item. If it's not in that item, look at the third item. If it's not in that item, look at the fourth item. And if it's not in our bucket of size 4, then it's not in this file. So it's more of a case of your position is an array of 4 items. And then it looks for item 1, item 2, item 3, and item 4, depending on how you search for it. So will we be asked to do collision handling using all types of collision handling, or will we be told which method to use? We will tell you specifically what method to use. So we will give you a table, we'll give you an empty table, and we'll give you a table of inserts. Now the table of inserts has to be done sequentially. You have to start at the top and insert them one by one in the order they are in the table given to you. And then you will insert them into the table that you will draw one by one. But we will tell you specifically. So you will most likely have to do about 3 collisions. So we will tell you to do one of these 5. So the main paper might be linear, separate, and bucket addressing. The SSA will probably be two pass, synonym, and separate overflow. And the special SSA will be a different thing. We literally we created a table like this with inserts, created a size for the file, and we took a dice and rolled the dice to see which one you'll be doing for the main SSA and the special SSA. So we really went at random, choosing 3 of them. It's more fair that way. I say more fair. It's fair that way. Because it's not us choosing the easiest, the most difficult one. It's us literally choosing at random which 3 for you to do. But I'm assuming that you are comfortable with all 5 of them. And it is online exam, so if you're struggling with the concept, you can always use this slide. You can go back to the slide just to double check whether you misunderstood something or not. Kind of why we did the collision handling today, because I wanted to set up these slides and just, instead of just giving you these 5 names and then discussing them one by one. So there is one more practical. It's not going to be a coding practical though. It's a bonus practical for the projects day that we'll be doing on Wednesday. So just as a reminder, projects day is on Wednesday. It's demonstrating the 3rd years, the honor students, and I think the top 3 or the top 5 second year students with their projects in Informatics 2B. The practical is basically a few questions. So it's going to be a questionnaire that you'll have to fill out about projects. So you'll have to either talk to some of the students or watch some of the presentations so that you can understand what is going on, so that you can answer the question. So it's literally just a questionnaire that you're going to fill out, and that's the last practical that you have. That's the last thing you're going to be submitting to us, excluding the students that still need to write the SSA, by the way. All right. Now, before we get to the other questions, because I'm pretty sure you have some questions, is there anything regarding collisions that you did not understand? Is there something that you want me to cover again? Like just open up your information. Is there something you want me to go over again? Are all of you comfortable with all 5 of the collision handling concepts? Two-pass file creation. All right. You can go through that one again. If you want, we can spend some time, because look, tomorrow we're doing a practical for the, not a practical, we're going through a past paper. So we're going to look at the questions and actually do the questions in the paper. So we can do this again, or we can take the table and do all 5 of them tomorrow afternoon. So just for for two-pass file creation. The two-pass file creation, let's use Excel. Let me show this to you in Excel. Maybe that will make a bit sense, or more sense to you. So we've got Porsche, Ford, and Jeep. So we've got position, and we've got model 0, 1, 2, 3, 4, 5, 6. We had Porsche, Ford, and Jeep. Let's just go Jeep, Ford, Porsche. Right. And then we have our insert. So what we need to insert is Audi, Hyundai, and Chevy. So with two-pass file creation, so let's go remove that. Let's just put it down here. Merge, merge, merge. Insert, left over, pass 1. And then we had Audi, Hyundai, and Chevy. So let's go 8, 10, 9, Audi, Hyundai, and Chevy. So what will happen is for pass 1, we'll go through them one by one. In this case, what we'll do is we'll look at Audi. Audi with our hashing algorithm would go to position 1. Position 1 is already filled. So Audi will not be placed. It's kept in the leftover pile or something we still need to look at. Hyundai would hash to position 3. Position 3. And Chevy will hash to position 2. So no issues there. They go directly into those posts. There's no collisions. If there were a collision, so let's say we add Tesla, so 16. If we look at Tesla, there is a clash. So Tesla would have to go into the leftover. So the idea is, if there is a clash, we keep them on one side. We first place the items that can be placed without collisions. That's pass 1. Then we do pass 2. Pass 2 looks at what we have already and keeps that. So it keeps what we have. Then it looks at the leftover container or the leftovers, and it now applies linear probing to that. So we've got Audi. Audi would have gone into position 1. So now we apply linear probing and say, okay, it's not there, not there, not there. Where is the spot? We place Audi. We go to the next one. So once Audi is dealt with, that goes out. We go to the next one, which is Tesla. Tesla would have gone to Chevy, but position 2, but that's already taken. So we apply linear probing. So not there, not there, not there. There is an open spot. We place Tesla. So what we expect from you in the exam is 2 of these tables. Table 1 to indicate that's the first pass, and table 2 to indicate that is the second pass. If you had to code this up in terms of your actual practical application, this would be one file. You'll go through the file once, look at things that can go in straight, and then go to your file again and look at whatever is left over and place them into the file. Okay, I can't see. Let me just go back to your question. Right. So Zagoya, is that okay for you now? Okay, perfect. Now, we're going to discuss collisions again tomorrow. Like I said, we're going to go through the past paper. So if you have an issue with any one of the specific collisions, just tell us, and then we'll do that one instead of the one that's in the past paper. Okay, that being said, I am running slightly over time here. So if you have any questions, I'm hoping that how I've gone through these and the way I set up the slide for you, that you'll understand each one of these a bit easier. It's a nice guide for you to go back to see how they were handled. That's why the first one has that kind of like point by point what's going on. And thereafter, kind of just indicate before insert and after insert. Right. If you have an issue, you can email us, you can post it on Discord. Like I said, we're more than happy to help you. You need to let us know if you're struggling with it. Please come to the TUT if you're struggling. In the TUT, we try and stick to the time. We're never under time. We always go over time. But that is so that we can always deal with the questions. But it's based on the live session. So during the TUT, we'll discuss a planned session. After the TUT, when we've discussed everything we wanted to discuss, we handle all the questions. So we don't always record the entire TUT, the additional questions, because we do run out of time, unfortunately, and we don't want the recordings to exceed the actual lecture time. So if you have any questions you want to discuss with us, please come to the TUT. Like I said, we normally stay after the time. You can ask Oliver and Basso and Goyo and Masondo, just a few names that I recognize here. They always stay like an hour afterwards, just so that they can ask questions and see how certain things are done in a bit more detail. Specifically, the odd things that we kind of don't show. So if you have questions, please come and ask them. If you can't make it to the TUTs, you can email us and we'll email you a response back. The emails are sometimes a bit slow. If you don't receive an email within at least 24 hours, please just email it again. It sometimes does get lost in our inbox, especially with the amount of emails we get. So if we don't respond to your email or to your message within 24 hours, please just post it or email it again so we can get to that. I can promise we will never intentionally just ignore a question. We'll always address the question. But just remind us if we don't, because we do sometimes forget. That being said, I hope you guys have a lovely evening further. Please make sure that you fill in all the reviews, your peer review specifically, your group feedback, which that's important as well. And just keep an eye on your exams. I don't know how Blackboard informs you about the module and peer evaluations, but please, I encourage all of you to do that because it really does help us in terms of seeing where we can improve. There's always space for improvement. Nothing is ever 100% perfect. So if you have any comments that you think that can improve the lectures, improve the recordings, or just improve the content, even the slides, please let us know. It really does help us. Right. That being said, I'll see you guys tomorrow afternoon in the tutorial. Those that are with Dr. Cottrell, he will see you tomorrow morning. Enjoy the rest of the evening or afternoon.